Wait a second. On the outside, 19th century medicine looked noble. University diplomas on the walls, Latin in medical records, confident prescriptions for bad humors and miasmas. But inside, there's a strange detail. A finicky device with cloudy lenses, mysterious little creatures in water, and one stubborn Hungarian doctor who changed everything you thought you knew about medical honor. Stick around till the end to see the moment when washing hands transforms from a whim into the line between life and death. But to understand why that moment took so long to arrive, we'll need to step back a couple of centuries, to a time when the very idea of an invisible enemy seemed absurd. In the mid-17th century, a doctor entering a sick person's home was certain where trouble came from. He could smell it. Disease had a scent. Rot, mustiness, decay. It hung in the air above swamps, rose from piles of filth in the streets, seeped from cellars where meat was stored. These poisonous vapors were called miasmas, and learned men were convinced they penetrated the body through lungs and skin, bringing plague, cholera, and fever. The logic was ironclad. Where it stank, people got sick and died. Drain a swamp or burn infected clothing, and the epidemic would retreat. Plague doctors wore masks with long beaks stuffed with aromatic herbs and spices, not for show, but to protect themselves from deadly air. Hospitals burned juniper and frankincense, fumigated wards with sulfur. All of this worked sometimes, but nobody understood why. Meanwhile, another system of explanation lived on, even more ancient. Doctors educated at universities memorized the works of Hippocrates and Galen. They taught that 4 fluids circulated in the human body: blood, phlegm, yellow bile, and black bile. Disease was an imbalance of these. Too much blood? Release the excess, and the physician would apply leeches or cut a vein. Excess yellow bile? Administer an emetic. Black bile accumulated? Laxatives and cleansing enemas. This theory of humors seemed flawless. It explained everything. Why people of different temperaments got sick differently, why the same illness passed easily through one person but killed another in 3 days. Every symptom found its place in this framework. And most importantly, the doctor always knew what to do. The system gave a sense of control, even if it was illusory. The most astonishing thing? It never occurred to anyone that the cause of disease could be invisible. Not fog, not smell, not an imbalance inside the body, but something so tiny the eye couldn't detect it. Understanding of the world was built on what you could see, touch, smell. If an enemy existed, it had to be visible, even if just as smoke, murky water, or pale skin. The thought that a drop of the purest water teemed with thousands of creatures capable of killing a person was beyond imagination. Antony van Leeuwenhoek sold fabric in the Dutch town of Delft. His shop's success depended on his ability to spot thread quality, weave density, and tiny flaws that customers would notice later and complain about. For this, Leeuwenhoek ground magnifying lenses, tiny glass beads he inserted into copper plates. By the mid-16th century, this was a standard craftsman's tool, nothing more. But Leeuwenhoek turned out to be a perfectionist. He ground lenses again and again, achieving greater clarity and curvature. By 1670, his best samples magnified 270 times, incredible power for that era. And one day, either from boredom or curiosity, he held under the lens not a piece of cloth but a drop of water from the barrel in his yard. What he saw turned his life upside down. In the drop, tiny creatures were swarming. They moved, spun, bumped into each other. Some were round, others elongated, still others twisted like little snakes. Leeuwenhoek wasn't a scientist, didn't know Latin, hadn't read medical treatises. He just looked and couldn't look away. He started studying everything, scraped plaque from his teeth. There were entire colonies of creatures there, more numerous than people in the United Provinces. Examined a drop of semen and saw tadpoles with tails darting through the liquid. Took water from a ditch, from a pond, from a rain barrel. Everywhere life teemed, invisible to the naked eye. He called them animalcules, little animals, and methodically drew, measured, and described them. In 1673, Leeuwenhoek began writing letters to the Royal Society of London, Europe's leading scientific club. The letters were naive, full of enthusiasm, without theoretical pretensions. He simply reported, "Look what I found." At first, they took him for an eccentric. But when society members repeated the observations and confirmed he wasn't lying, Leeuwenhoek was elected a member. His drawings and descriptions began to be published. The microscopic world stopped being one Dutchman's secret. But scientists' reaction was strange. Yes, they acknowledged, tiny creatures really do exist. It's a fact of nature, curious and amusing. But it didn't go further than that. Nobody asked, could these little creatures cause diseases? Nobody connected them with rot, contagion, epidemics. Animalcules remained a curiosity, a toy for naturalists examining rarities. Why? Because between observation and understanding lay a chasm. Leeuwenhoek saw microbes in water, in saliva, in infusions. But he saw them in perfectly healthy fluids and in spoiled ones. They were everywhere, which meant they weren't responsible for anything specific. There was no way to distinguish a harmless microbe from a deadly one. There was no concept of infection in the modern sense. And most importantly, there was no technology to prove the connection. The 17th century microscope showed moving creatures but didn't explain who they were or what they did. It was a book in an unknown language. Doctors continued treating miasmas and humors, while Leeuwenhoek's animalcules remained a curiosity in naturalists' cabinets. Between the discovery and the medical revolution stretched 2 centuries, and millions of deaths that could have been prevented. After Leeuwenhoek's death, the microscope didn't disappear, but it turned into a toy for wealthy hobbyists. Aristocrats ordered elegant instruments in leather cases, showed guests a flea the size of a fist, marveled at patterns on a fly's wing. But the tool never made it into medicine. For almost 200 years, doctors got by without it and considered this normal. The main problem was technical. 18th century microscopes produced murky, distorted images. Glass contained bubbles and impurities. Lenses were ground imprecisely. 2 defects killed any usefulness. Spherical aberration blurred the edges of objects, while chromatic aberration colored them with rainbow halos, like a cheap prism. Making out details of tissue or fluid structure was nearly impossible. A doctor who tried looking through such a device saw colored blobs and smears, and reasonably decided it was a waste of time. The instrument itself was awkward. Early compound microscopes, with multiple lenses to boost magnification, stretched into tubes almost half a meter long and weighed considerably. Adjusting focus, catching light, securing the specimen required skill and patience. A simple microscope with one lens, like Leeuwenhoek's, gave a better picture but magnified weakly and was only good for the largest objects. Most doctors saw no point fussing with a finicky device when you could diagnose by pulse, tongue color, and the smell of discharge. But technology wasn't the main issue. Even if the microscope worked perfectly, scientists didn't know what to look for. The theory of spontaneous generation dominated. It was believed that microorganisms arose on their own from rotting matter. Leave a piece of meat on the table. In a day, worms would appear in it. Pour water into a barrel. In a week, animalcules would be swimming there. The conclusion seemed obvious. Life is born from dead matter under the influence of heat, moisture, and air. This idea went back to Aristotle and over 2 millennia had become part of common sense. If microbes appear on their own, then they're a consequence of disease, not the cause. Rot spawns them, not the other way around. The logic closed in a loop. Miasmas spoil the air spoils tissues, spoiled tissues spawn microbes. The circle of proof looked flawless, and no microscope observations shook it. The third wall was the authority of tradition. Medical faculties across Europe taught from treatises written centuries ago. Professors read aloud from Galen and Avicenna. Students took notes, memorized, passed exams. A doctor who got his diploma knew the theory of humors and miasmas by heart. To suggest all this was wrong meant crossing out years of study and questioning teachers' competence. The idea of invisible creatures causing disease sounded like heresy or quackery, something from alchemy or astrology, not serious science. By the early 19th century, the microscope remained the domain of naturalists studying plant and insect structure. Physicians ignored it, and while they ignored it, 1 in 10 mothers died in Europe's maternity wards. In 1846, a young Hungarian doctor named Ignaz Semmelweis got a position as assistant in the maternity ward of Vienna General Hospital. He was 28, had just finished university, and burned with desire to help people. The first thing he saw was horror. The hospital had 2 maternity wards located in adjacent wings of the building. The first was staffed by doctors and medical students. The second by midwives. Formally, conditions were identical. Same rooms, same beds, same food. But mortality statistics differed threefold. In the doctor's ward, 16% of women died from childbed fever. In the midwives' ward, about 6%. Pregnant women knew this and begged on their knees not to be sent to the doctors. Semmelweis started looking for the cause. He checked everything: ventilation, mothers' positions during labor, techniques for receiving infants, even the timing of the priest's rounds with last rites. Nothing explained the difference. One day in the hallway, it hit him. Medical students came to the maternity ward straight from classes in the anatomy theater, where they dissected corpses. Midwives didn't touch corpses, they were trained on mannequins and living mothers. Semmelweis formulated a hypothesis. Students' hands carried cadaverous particles, some decomposing substance from dead bodies onto the living tissues of mothers. He couldn't explain the mechanism, didn't know about bacteria, never saw the pathogen. But the pattern was glaring. In 1847, he introduced a mandatory rule. Before entering the maternity ward, everyone must wash their hands with chlorinated lime solution, a caustic liquid that breaks down organic matter. The result was stunning. Within a few months, mortality in the first ward dropped from 18% to 2%, lower than the midwives. Semmelweis was ecstatic. He'd saved hundreds of lives with the simplest action. It seemed the medical world should have fallen at his feet. Instead, they laughed at him. Colleagues found the idea insulting. Doctors were educated gentlemen who'd studied at universities for years. How dare anyone suggest their hands were a source of contagion? This was an accusation of slovenliness, of murdering patients. Professor Johann Klein, Semmelweis's superior, forbade him from publishing results. Other doctors called him an upstart and ignoramus. One colleague publicly declared, "I don't believe there can be anything on my hands harmful to patients." Semmelweis couldn't defend himself. He was a poor speaker, didn't write articles, couldn't persuade. He simply knew he was right and didn't understand why others couldn't see the obvious. He began writing angry letters to professors across Europe, accusing them of murdering mothers. They considered him insane. In 1849, his contract wasn't renewed. He went to Budapest, where he tried implementing his method in a local hospital. Mortality dropped there too, but there was no recognition. By the early 60s, Semmelweis fell into depression. He watched women continue dying in childbirth because of colleagues' stubbornness, and it drove him mad. In 1865, he was tricked into entering a psychiatric asylum. 2 weeks later, he died, according to one version, from beatings by guards, according to another, from blood poisoning after an injury. He was 47. A few years later, Louis Pasteur and Joseph Lister would prove him right. But Semmelweis would never see it. By the mid-19th century, the microscope began slowly emerging from naturalists' cabinets. In Paris, a man bent over it who wasn't actually a doctor but a chemist. Louis Pasteur was interested not in diseases but in wine and beer. French winemakers complained. Entire batches were spoiling, fermenting incorrectly, sour odors destroying harvests. For France, this wasn't just a gastronomic problem but a blow to the economy and prestige. Pasteur began examining drops of good and spoiled wine under the microscope. In one, he saw orderly rows of yeast, oval cells neatly dividing and working for the winemaker. In another, chaos from foreign creatures that hijacked the must and drove it toward vinegar and rot. For Pasteur, this was a moment of revelation. Fermentation isn't done by the liquid itself or some vital force, but by specific organisms. Good wine was linked to certain microbes, spoiled wine to others. The next step was a blow to the very idea of spontaneous generation. Pasteur set up his famous experiment with swan neck flasks. Nutritious broth was poured into these vessels and boiled, killing everything alive. Air entered freely, but dust and spores settled in the bend of the neck. The broth stayed clear for months. You only had to tilt the flask so the liquid touched the sediment. Within days it would cloud and come alive. This was visual proof. Microbes aren't born from nothing, they come from outside. At first, these experiments were seen as an important milestone in chemistry and biology, but not as a medical revolution. Pasteur took the next step himself. He undertook studying silkworm diseases that plagued French silk producers and found specific microscopic organisms in the insect's tissues. Then he switched to anthrax in sheep and cattle, then to rabies in dogs and humans. In each case, he tried linking a specific microbe to a specific disease, and gradually this connection stopped seeming fantastic. In 1885, a boy named Joseph Meister was brought to Pasteur's laboratory. He'd been bitten by a rabid dog, and the family understood. Without intervention, the child was almost doomed. By that point, Pasteur had already experimented with weakened rabies pathogens on animals, but the method hadn't been tried on humans. Technically, he wasn't even a doctor and had no right to treat. Nevertheless, after consulting with colleagues, he decided to try. The boy was given a series of injections of weakened material, day after day. Joseph survived. This story had the effect of a bomb going off. For the first time, a person already almost condemned was saved using a pre-prepared, weakened enemy. The word vaccine already existed from Jenner's experiments with smallpox, but here the mechanism was explained far more precisely. The microscope stopped being just a magnifying glass. It became a weapon in the chain from observation to intervention. See the invisible enemy, understand its behavior, alter it, and use it for protection. If Pasteur showed that microbes could cause disease, Robert Koch proposed exactly how to prove it. The German doctor, who started his career as a country physician, possessed a rare combination of persistence and technical ingenuity. He understood. Microscope observation alone wasn't enough. To accuse a microorganism, you needed to present not just a portrait but a chain of cause and effect. Thus appeared Koch's famous postulates. First, the pathogen must be found in all sick individuals and absent in healthy ones. Second, it must be isolated in pure culture, meaning grown separately from other microbes. Third, this culture must cause the same disease in a healthy animal. Fourth, from this animal you must isolate the same microorganism again. This scheme seems obvious today, but back then it was a breakthrough. Disease stopped being an abstract, spoiled humor or miasma and became a concrete chain of events. In 1882, Koch announced the discovery of the tuberculosis pathogen. He perfected methods of staining and fixing specimens so that the thin rods of tubercle bacteria became visible against tissue background. Doctors saw for the first time the face of one of the century's most terrible diseases. On the slide, chains of tiny rods neatly highlighted with dye. For a contemporary, this was almost a photograph of a murderer caught red-handed. Tuberculosis was followed by other triumphs. Koch and his students isolated pathogens of cholera, anthrax, tetanus. Doctors with microscopes and boxes of glass slides traveled to laboratories across Europe and America. They took smears, stained them, grew cultures on gelatin and potato slices. In every disease, they searched for its own underground agent. And increasingly, they found them. By the end of the 19th century, The microscope transformed from a cabinet of curiosities into an essential diagnostic tool. Now it wasn't a toy or a symbol of learning, but a way to see a real object on which a patient's life depended. But this hunt for microbes had a human cost too. Each discovery meant acknowledgement. Until that moment, doctors had been treating almost blindly. Where yesterday they spoke of weakness, heredity, or bad climate, now there appeared a strict formulation. Specific pathogen, specific transmission route. Old explanations retreated, and with them went the feeling of familiar order. Medicine entered an era when disease wasn't a vague imbalance but a collision with an invisible yet entirely material enemy, seen clearly for the first time through a microscope's eyepiece. When microbes stopped being an abstraction and got their names and portraits, surgery suddenly saw itself in a new light. The 19th century operating room was a place where main attention went to speed and steady hands, but almost no thought to invisible cleanliness. A surgeon could move from dissecting a corpse to an amputation without a break, wiping his knife on his apron. Patients often died not from the operation itself but from subsequent purulent complications, which were seen as almost inevitable fate. British surgeon Joseph Lister carefully read Pasteur's work on microbes and fermentation. A thought struck him. If spoiled wine is ruined by microorganisms from the air, then why not assume that a wound also sours because of the same invisible creatures? Lister began treating wounds with carbolic acid solution, irrigating instruments with it, applying bandages soaked in the substance to sutures. Mortality after operations in his ward dropped several times over. What was once considered inevitable putrid fever turned out to be a preventable complication. Antiseptics gradually transformed into a system. By the end of the 19th century, hospitals introduced mandatory boiling of instruments and began using steam sterilizers. The habit appeared of not just washing hands but thoroughly washing and ironing linens, bandages, and gowns. Glass syringes, metal scalpels, needles, all now passed through boiling water or steam before touching a patient's body. A mistake in preparation was no longer seen as an annoying trifle but as a real threat. Interestingly, even the rubber gloves familiar today were born not only from concern for patients but from a very human story. American surgeon William Halsted ordered them for an operating room nurse whose skin suffered from constant contact with antiseptics. The gloves quickly proved convenient both for protecting doctors' hands and as an additional barrier between skin and wound. Gradually, they became standard. The hospital environment itself changed too. Where just a few decades earlier dozens of patients with different ailments lay side by side in large wards, separate rooms and isolation wards appeared. Walls began to be covered with smooth tile, easier to wash and disinfect. Ventilation, lighting, placement of sanitary rooms were thought through. Hospital architecture became an extension of germ theory. Every corner, every surface was examined from the standpoint of how invisible disease agents might linger and spread there. Acceptance of germ theory wasn't a quiet evolution. For many people, the late 19th century became a time of real discovery of invisible enemies. Newspapers and popular pamphlets eagerly picked up the theme. Illustrations drew microbes as monsters lurking in a glass of water, on a door handle on a child's toy. A new form of anxiety emerged. If danger is invisible, it could be everywhere. People began shaking hands more cautiously, looking suspiciously at shared towels and mugs in taverns. Merchants quickly realized this fear could make money. Soaps with loud promises to kill all germs appeared on the market, along with disinfecting powders and sprays for treating clothing and furniture. Ads emphasized that only these products could protect against invisible killers. From a scientific standpoint, some of these products genuinely helped improve hygiene. But along with real benefit, an idea of total danger seeped into public consciousness, where any trace of dirt was perceived as an almost deadly threat. Resistance came not just from ordinary people but from some doctors too. For an old-school physician, accepting germ theory meant admitting he'd been unwittingly causing harm for many years. That his cleanly washed but non-disinfected hands could have been the cause of someone else's tragedy. This was heavy knowledge, natural to brush off. There were those who relied on miasmas and humors till the end of their lives, considering germ fanatics a fashionable fad. The medical community split. Some quickly restructured their practice around new knowledge, others accepted it slowly and reluctantly. Thus, a dual image of the microbe emerged in culture. On one hand, as a real, concrete disease agent that could be seen through a microscope, grown in a dish, and therefore learned how to stop. On the other, as a symbol of invisible danger from which people wanted to protect themselves at any cost, even at the cost of excessive sterility and constant anxiety. Right at this intersection of science, fear, and habits, the world we still live in today began to form. Understanding that diseases could be transmitted through water and food took the fight against microbes far beyond hospital walls. City authorities in major European capitals began looking at their streets and rivers with different eyes. Ditches where waste had been dumped for centuries became sources of potential contagion. Projects for centralized sewage systems, closed collectors, and treatment facilities gradually appeared. Plumbing stopped being just a convenience and became an element of health protection. Clean water from a protected source was viewed as medicine against a whole set of infections. Habits around food changed too. People learned to treat milk, meat, and fish not only as products but as possible carriers of microbes. Pasteurization technologies emerged, allowing heat to kill most dangerous organisms without destroying the product itself. Canning and cold storage got new explanations. It wasn't about sealing freshness, but about slowing or stopping the growth of invisible inhabitants that caused spoilage. A refrigerator in the home became not just a symbol of convenience but part of an invisible barrier between humans and numerous foodborne infections. In parallel, a new figure was born, the laboratory doctor, the bacteriologist. If previously diagnosis was made mainly from the patient's story, appearance, and simple tests, now cultures, stains, and microscopy came into play. Laboratories appeared in hospitals and city sanitary epidemiological stations where cultures from water, blood, and sputum were grown. There, in silence under lamplight, research doctors searched for the specific pathogen behind each disease outbreak. Medicine gained a new language. Instead of vague formulations like fever of unknown origin, specific microbe names were increasingly heard. By the end of the 19th century, the microscopic revolution in medicine could be considered complete. But its waves reach us even now. The simplest gesture, washing hands, became something like a symbol of scientific medicine. Behind this action stand the fates of people like Ignaz Semmelweis and decades of debate, whether to give significance to what can't be seen at all. Every modern hygiene reminder, every poster in a public place is a distant echo of that struggle for recognition of the invisible enemy. The microscope itself has radically changed over this time. Instead of heavy tubes with cloudy lenses came complex optical systems, then electronic and even atomic force instruments allowing examination not just of bacteria but viruses, individual molecules, structures inside cells. From microbiology grew entire branches, virology, immunology, genetics. But the principle remained the same, the attempt to see what's hidden from ordinary sight, and through this understand the nature of disease. This story has a paradoxical side too. The more humanity learns about microbes, the more ambivalent the attitude toward the surrounding world becomes. On one hand, respect grows for our own microflora. It becomes clear that without množstva-friendly bacteria, our intestines, skin, and immune system couldn't function normally. On the other, irrational fear of any dirt, dust, or stain on a surface intensifies. Bottles of antiseptics and disinfecting wipes have firmly entered daily life, and the drive for absolute sterility sometimes begins to harm, depriving the body of natural stimuli for training its defenses. The history of the microscope and microbes isn't just a story about techniques and discoveries. It's an example of how slowly and difficultly views on the invisible change. 200 years from Leeuwenhoek's first animalcules to the generally accepted germ theory, that's the price for learning to see the connection between tiny creatures under glass and the fates of people in hospital wards, on city streets, in their own homes. And every time a person turns on a tap with clean water or washes hands after being outside, they unknowingly continue this story. Imagining that microbes exist was easy. What was hard was accepting that millions had already died because of disbelief in them. Every unwashed surgical instrument, every hand not scalded with antiseptic. This isn't an abstract mistake, but someone's life that never happened. But it was on this pain that new medicine grew. And whenever a person simply goes to the tap and washes their hands, they unknowingly put a period in a 2-century-long argument. The invisible matters.